we can do all the verification. This is really a horrible task for SLICAP, because here I put capacitors in, and these capacitors are assumed to be shorts for the noise. So by design, I assume that these components do nothing with the noise. So I better leave them out, because what SLICAP does is it symbolically calculates the noise, and if I want to have an RMS value, it symbolically integrates the noise. And you can imagine, if you put all kind of capacitors and inductors in your circuit, that this symbolic integration becomes very difficult. And it cannot always give you an answer. But if you wait long enough, SLICAP will give you an answer. It works. I have the output files. So this is for the noise verification. And we find 2.4 dB noise figure if I assume 500 kilohertz bandwidth with multiplied by pi over 2, which is a noise bandwidth if it is first order, but that's an estimate because I think the thing will not be first order, of a little bit more than 500 kilohertz, pi over 2 times 500 kilohertz. Included is here already components for phantom zeros. Also in the noise, you can leave them out of the noise evaluation. I just did it. I don't know really why. At the end, I just added everything to check if SLICAP could manage such a circuit, and it can. So for the biasing, we put in the numbers like the standard deviation and the values of the offset and the bias. And this is the model that I use. All component tolerances are assumed 1% for 3 sigma values, and the standard deviation at the output voltage then calculated with SLICAP is about 10 millivolt, which is well within the range of 200 millivolt before everything will clip. The frequency response, that's a nasty thing, because now we have to investigate this, and you see this output impedance is not making the thing very simple. How many poles would we have? Well, I would say 1, 2 poles, 3, 4, 5, and then I'm at this point. This one is a, 6, 7, and this one is a loop. So I expect 7 poles and a number of zeros. So, and this causes resonance. So in the loop, we will already find, with this small resistor here, we will already find complex poles. And this is the result. Wow, I didn't study it before, but you see, SLICAP nicely gives you 7 poles, 2 of which are complex. And they arise from resonance between this capacitor and this inductor. And you can check where the other comes from. And if we then make the root locus for our amplifier, then we see that the poles are moving closely, these complex poles, closely to the imaginary axis. So I'm expecting a lot of ringing and almost unstable behavior. So this is the dominant pole, and these are non-dominant poles. You see here, the frequency here is 3 megahertz, and this is less than a megahertz. So the bandwidth of the amplifier will be less than a megahertz. But at about 3 megahertz, I find non-dominant poles. So here you have the loop gain. Oh, sorry, that is, they almost stay there. So let's see. I have dominant poles, and this is the gain. The gain is a little bit more than 90 because I took other resistor value, and you see this very high complex number here. These are not the dominant poles. It is sorted on the real part, as you see here. So these are not the dominant poles. The dominant is like 800 kilohertz, you see, 823 kilohertz, and this is at 3 megahertz. So these poles are non-dominant, but they can make the amplifier unstable if the loop gain is a little bit varying. So I really have to do something about it. Let's see how it looks. So here you see that the loop gain is the magnitude of the loop gain, the black one, the black passes 0 dB at, well, let's say about this is 800 kilohertz here. And the influence even there of this complex pulse is large because it's still fine peaking in the servo function. The asymptotic gain is just a flat line, so the model is correct. So we have to do something about this. And you see, if you make the step response of the uncompensated amplifier, well, if you look clearly, you see that this is damping. The amplitude is getting less, but the step response is really this ringing is this frequency. You can count it. Yes, this is about 4 megahertz, 3 megahertz, 2, 3, which means that this is 1 microsecond per division. So this is 1 microsecond. So I must have 3 cycles in 1 microsecond. 1, 2, 3 cycles about in a microsecond. So that's about 3 megahertz. Let's do some frequency compensation. And I suggest 2 phantom zeros. 1 phantom zero here and 1 phantom zero here. And I'm not going to calculate it because it's just too complex. The thing is that we have learned where we can implement phantom zeros and we can use SLICAP to optimize their values. And I don't expect you to calculate for such a high order system exactly the zeros that you need. Let's just put 2 phantom zeros in and see if I can tune it with this. And here you see I now tuned the complex pulse to having a Q of less than 0.7. And the bandwidth is these are on the zeros. Yes, this is because of sorry, this is the loop gain, so I cannot adjust the bandwidth. And here you have the new root locus plot. And now you see this looks far more attractive because now if the loop gain for some reason changes, they're not going to the complex plane, but let's say only the Q of these poles is changing a little bit. So this is the dominant pole. So the bandwidth is limited to, well, this will be maybe like what it is, like 700 kilohertz or so. And then here we have at 1.5 megahertz, somewhere we have a little bit, we have extra 2 complex poles, but they are almost in Butterworth, you see, almost in Butterworth. So this looks pretty nice. We have 600 kilohertz bandwidth, 666. Well, I estimated 700 from here. And the 2 poles now have a Q of lower than 0.7. You find another 2 at 20 megahertz, also with a low Q, but they're not on the plot here. But you can make them on the plot if you want. So here you see the result. The result now is a nice, the asymptotic gain drops and the loop gain will have zeros. So the phantom zeros, the zeros are not visible in the gain. And here you see nicely the gain is dropping down. It's not Butterworth, but it's the best we can make here. And this is the step response of the compensated amplifier.